Namaste, good morning, good evening, good afternoon, wherever you are. I am Animesh Das, a final year undergraduate student pursuing my bachelor's and master's degree in electronics and communication engineering at the International Institute of Information Technology, Hyderabad, India. Today I'll be presenting the paper titled Using Miniature Setups and Partial Streams for Scalable Remote Labs, co-authored with K.S. Viswanadh, Rishabh Agrawal, Akshit Gureja, Nitin Nilesh, and Dr. Sachin Chaudhari. In this presentation, I will give a brief introduction about remote labs, the motivation behind our work, and the contributions made through this paper. Next, I'll talk about the use case experiment, the two kinds of setups that were created for this, the methodology for partial streams, the results obtained, and finally conclude. Our project topic mainly focuses on delivering practical knowledge using IoT. No student can miss out on the practical knowledge gained through laboratory experiments, as this knowledge leaves a long-lasting impact that is also vital to one's career. However, COVID-19 forced us to stay at home, making labs inaccessible to many. A simple solution was to use powerful IoT technology. IoT means Internet of Things, and remote labs is one such concept where actual physical experiments can be retrofitted using sensors and actuators such that they can be controlled from anywhere on a web-based dashboard that also displays the results to analyze. In other words, it is the use of computer networks and internet communication protocol to provide remote access to real live lab apparatus to conduct various experiments as deemed fit for the apparatus. A system like this can host a wide range of experiments from a variety of disciplines like engineering, physics, chemistry, and biology. It is useful if it is not possible to access proper laboratory facilities in person. We have seen that components have become expensive since the global silicon shortage that ensued because of COVID-19. I remember having bought a Raspberry Pi 3B in 2018 for 5,000 rupees and the price shooting up to more than 10,000 rupees as of April 2023. Thus, it becomes important that setups be optimized for component count and cost. Besides, we do not like it when electric bills are high, do we? So we would want current and energy consumption to be as low as possible for lower electric bills. This is why we propose miniaturization. Also, we wouldn't want to wait for the setup to be free for use. It is therefore important that we keep two or more setups ready, and keeping in line with the theme of component reduction, we want to do this with as few components as possible. Hence, partial streams. An added advantage of the miniature setup that we are proposing here is that we don't need a technician to install a setup like this. We can install these ourselves. Basically, what we are proposing here is IKEA, but for science experiments. Let us look at the contributions from this paper. A miniature setup is proposed for the use case of the vanishing rod experiment. A methodology for generating partial streams is proposed, which involves using a single camera for multiple setups and is tested with two miniature setups. The proposed system with miniature setups and partial streams is compared with the traditional system of a lab scale setup with a dedicated camera stream. All of the above setups are deployed in our remote labs at IIIT Hyderabad. The vanishing rod experiment is a demonstration of Snell's law, which states that when light travels through media, the product of the refractive index n of the medium and the sine of angle of traversal with respect to the normal between two media, theta, remains constant. Thus, n times sine theta remains constant across all media. To demonstrate, we required two beakers, one filled with sunflower oil, the other filled with water, and two glass rods. It is observed that one of the rods, in fact the one dipped in oil, seems to vanish when dipped. An explanation for this is because oil and glass have almost the same refractive indices, but water and glass do not, which is why oil and glass, when kept together, seem to be the same medium. Hence, it feels like glass vanished into oil. Whereas that's not the case with water and glass. To perform the vanishing rod experiment, a lab scale setup is created. This setup is controlled by a Raspberry Pi, which is connected to two stepper motors and the respective motor drivers, one for each rod to drop and pull the rods at will. Attached to the Raspberry Pi alongside these motor drivers is a Pi camera, which provides the live video feed for the setup. Below the rods are two beakers, each with 500 ml capacity, one filled with oil, the other filled with water. The dashboard has two buttons, up and down, which when clicked result in the rods being pulled up and dipped down respectively. The default configuration of the setup has both the rods up above the beakers, and this is what will be obtained when recalibrate is clicked. This dashboard uses Blink for device actuation and YouTube for streaming. When the user clicks, let's say, the up button, the prompt is pushed to FiCloud, which sends inputs to the Raspberry Pi, which then sends the control signal to the motors to pull up the rods. When the rods start to pull up, an acknowledgement is sent to Raspberry Pi, which forwards it to FiCloud, which then forwards it to the dashboard. Simultaneously, the Raspberry Pi also gets live feed from the camera of the experiment and sends this live feed to YouTube, which then pushes it to the dashboard. The miniature setup using a single motor controlled by an ESP32 to move the rods up and down. The beakers are also smaller, both 50 ml capacity, and use the same oil and water as before. Since it uses a single motor, a rod holder can be used to balance the rods and hold them in place. The movement slit ensures that the rod holder does not wobble. Instead of cotton thread, a thinner, shorter fishing line thread is used, which is why it's hard to spot here. Believe me, even I tried. The spool for the same, along with the humpback I-beam, the pulley holders and the rod holder are all 3D printed, and the entire setup can be assembled like Legos. Note that the microcontroller here only takes care of the motors. We still need the Raspberry Pi for video live streaming the experiment. And that's also an advantage, that the video live streaming the video live streaming aspect is separated from the setup, which opens up the scope for generating partial streams for multiple setups using a single camera. Let us look at the methodology for partial streams. Let us consider that there are n setups kept in front of the camera. Then the camera captures the view and the frame is then passed through the crop function. The n subframes so obtained are pushed to n virtual video streaming devices generated using Video for Linux 2.0. FFmpeg is used to capture the feed in each virtual video streaming device and push it to its respective YouTube stream key. Once these streams are on YouTube, the embeddable streams are pushed from there to the dashboard. This entire workflow is taken care of by the Raspberry Pi. The base function for generating partial streams, that is the crop function, involves these operations on a single frame. First, the frame is cropped to isolate the region of interest. Then n endpoints are marked horizontally to indicate where to cut. And finally, the image is chopped to get n subframes. It is assumed that the split can be made only about one axis, but can be generalized to make it about multiple axes. Let us bear in mind that before miniaturization and partial streaming, the software flow had the Raspberry Pi handling both actuation and live stream. Hence, one camera could show only one setup. Now that both are applied, actuation is taken care of by the respective ESP32 boards, while live stream for multiple setups is taken care of by one Pi camera module attached to a Raspberry Pi. As a result of this modification, now two or more users can use the same experiment dashboard with different setups. This video and this video are actually from the same video frame. Let us look at the results. The idle state of the setup is the state when no control signal response is observed. The control state of a setup is when the control signal is responded to. In both the plots, the peaks denote the control state. In case of the vanishing rod setup, control state is when the rods are either being pulled up or being dipped into the beakers. The blue plot represents the current consumption for the miniature setup, while the orange one represents that of the lab scale setup. In both the control state and idle state, it is observed that the current consumption of the miniature setup is lower than that of the lab scale setup. It is also noted that the control state lobes in the blue plot are narrower than that in the orange plot. An interpretation of this is that the control state window for the miniature setup is shorter than that of the lab scale setup. This can be explained by the smaller dimensions leading to shorter period for dip down or pull up actions in case of miniature setup as compared to the lab scale setup. Here is the comparative data for energy and current consumption for the cases of the lab scale setup and the miniature setup. As is observed from the table and previously discussed in the plot as well, the idle state current for the miniature setup is 1/6 that of the lab scale setup. The control state current value for the miniature setup is less than half that of the lab scale setup. Also to be noted is that the control state current for the miniature setup is lower than the idle state current for the lab scale setup. This is due to the shift to ESP32 from Raspberry Pi as controller for the motors. Thanks to the lower current values, the energy consumption per 100 use cycles per day is reduced to 1/6. Let us look at the component cost table for two setups, for 2 units of each experimental setup. It is observed from the table that the total cost in case of the miniature setups is lower than that of the lab scale setup. It is to also be noted that the majority of the money in both cases is spent on the Raspberry Pi and Pi camera together. If streaming were not to be considered, the miniature setup wouldn't require a Raspberry Pi and Pi cam, hence the actuation component cost would be almost 1/5 that of the lab scale setup. The total cost for 3 setups in case of lab scale is up to 43,000, while that for the miniature setups is 19,000. For 4 setups, the total cost would be 57,000, while that of the miniature setups is about 21,200. To summarize the paper, a cost-effective approach for scaling of remote labs is proposed. This approach uses miniaturization, image processing techniques, and partial streaming and is evaluated through the vanishing rod experiment where both the miniature and the lab scale setups are compared. The cost effectiveness of this approach is evaluated and it is observed that power cost is reduced to 1/6 and actuation component cost to 1/5. This is achieved through use of a single camera for live stream of multiple setups and through miniaturization. These are our major references, 3 of them. These, apart from the major references, are 12 other references. None of these are being discussed in the interest of time. Thank you for your patient hearing. I would like to open the floor for questions if any. I am also reachable via email here. Namaste.